Greetings and welcome. In today's video, I'm going to be doing a review of real exponents. So all of the examples and properties that I'm applying today, I will not be deriving, I will not be explaining necessarily where they come from. This is a review video specifically for students that have seen all of those before, and I'm just compiling them all together. This is actually a kind of introductory lesson in a chapter for pre-calculus students. So typically all of these properties are taught in an Algebra 2 equivalent. So I'm just going to do a whole bunch of examples and explain them as I go, and hopefully by the end of it you'll remember how to do all of these properties and whatnot. So let's see, let's just look at these, and most of these problems we're just going to be straight up simplifying. So here I've got a whole bunch of powers, some being multiplied, divided here. And they all happen to be of the same base. Because these are of the same base, I can apply some properties. So the first one that I'm going to do is I'm multiplying two things of the same base, so I can add these exponents. So that's 2 to the 4 plus 8, right? And 4 plus 8 is 12. Now, you wouldn't normally write that step, but I just want to write it for sake of visual to my verbal explanation. And that is now a combined kind of combine the exponents there. Now I'm also dividing two things of the same base, and somewhat symmetrically in property to what we just did, I will now subtract the exponents. And when I do this, I actually always recommend that you subtract the smaller from the larger, and then leave your answer in whichever numerator or denominator you happen to be in. So the larger's in the numerator, so I will have 2 to the 12 minus 5. And I will get 2 to the 7th. And then if I wanted, I could actually evaluate what 2 to the 7th is, which is 128, like so. So there's two properties that were applied there, the product of powers, in which you added the exponents, and the quotient of powers property, in which we subtracted the exponents. So let's keep cruising right along here. So what if I've got 2/5 to the negative first exponent? Now, first property I'm going to apply is the power of a quotient. It turns out you can actually distribute an exponent over multiplication or division. Now, a common mistake in mathematics is trying to distribute it over addition or subtraction, which is super illegal. So do not do that one. I did not tell you to do that, right? So I would distribute this exponent to both the top and bottom. Power to a power, I'm actually multiplying these, technically had positive 1 exponents, little invisible ones to begin with. So now I've got some negative exponents, and it turns out a problem is not simplified if you leave negative exponents in it. And the way we deal with negative exponents is either reciprocating, or the way I like to think about it is we'll move this one downstairs and we'll move this one upstairs, making its exponent positive. So this will be 5 to the positive first, or positive 1, over 2 to the first, right? So 5 halves would be my answer, right? And now they have positive exponents when they do that, right? So negative exponents, you just switch the location. Let's see, next one. Here we go. Let's throw some variables in here. What if I've got s to the second, t to the third, all to the fifth? So here I've got a product of powers, and I've also got it's all being raised to a power, so power to a power property kind of. And like I said a moment ago, you can distribute over division. You can also distribute over multiplication. Now I just want to point out here that notice I'm not going to add the 2 and the 3 here like I did up here with the 4 and the 8, specifically because these bases are not the same. Alright, so that property only applies when the bases are the same. So here I'm going to distribute, and I will get s to the 2 times 5 times t to the 3 times 5. Alright, so power to a power property, you multiply exponents. So that's s to the 10th times t to the 15th. And that would be simplified there. Let's see, next, what if I've got x to the 3rd y over x to the 4th all to the 3rd? So the first thing I'm going to do here is apply the power to a power property. So I will distribute there, so to speak, and multiply those. So that's x to the third y over x to the 12th. And now I can't combine the y. The y does have a positive 1 exponent though, but it's not the same base as the other ones. But I am going to, like I said earlier, subtract the smaller exponent from the larger. If I subtract it the other way, I'd end up with a negative exponent and then have to apply a second property to simplify it. So in my numerator, I'd be left with y, and in my denominator, I'd have x to the 12 minus 3. And like I said earlier, you don't have to write that step. That could be done in your head. That's going to be x to the 9th. I was just worried there for a moment. What if I did that wrong in my head? That would be embarrassing. So let's see. Let's keep going. So now let's consider, what about fractional exponents? And it turns out fractional exponents can be written as radicals. But there's a couple ways to deal with it. So 125, let's say I've got the number 125 raised to the 1/3 power. Now in this case, I could do some tricks to simplify this. I could think of 125 as being 5 to the 3rd, all to the 1/3 power. And then using my distributive property, right, I would have 5 to the 3 times 1/3, which is 5 to the 1st, or 5, right? So there we go. The other way I could think about this, kind of alternate universe situation, a 1/3 exponent is the same as a cubed root. Okay? And then the cubed root of 125 in this case simplifies right away to just be 5. So the denominator of an exponent becomes the index of a radical. Alright, so that's kind of a property of rational exponents there. So let's see, still moving right along here. Let's see, what if I've got 81c to the 4th, all to the 1/4 power? So whether I work with these in terms of exponents or break them into radicals, it technically doesn't matter. I'm going to do some simplification here for first. Let's see, 81 can be written as 3 to the 4th times c to the 4th, all to the 1/4 power, and then I would distribute here. Or I could take 4th roots if I wanted. So that would be 3 to the 4/4 times c to the 4/4, and that would be 3c, right? So that simplifies like so. And actually, one thing I just realized. I do have to be careful when taking roots or fractional exponents of variables. I have to consider the signs of those things. And I think I technically have written a wrong answer here. Let me do an aside note of what is the 4th root of c to the 4th. And let's just do a sign analysis of this. So the value of c itself, c could be any number, right? C is just some number. It's positive, negative, 0, right? One of those. Now c to the 4th is specifically going to be a positive number. And the 4th root of a positive number, because this is even, you can take an even root of a positive, but an even root of a negative is going to be imaginary. So if we were restricting this to just real numbers, the 4th root can only be taken of a positive, and it is a principal root in this case, where it's only going to give you your positive root back. So the 4th root of c to the 4th is actually also, we're expecting it to be positive. We need it to be positive. However, when I took that here, I said, oh, that's just the same as c, which isn't necessarily true because the original c could have been negative. So what I have to do is add some absolute values around that in order to account for the fact that I'm forcing c to be positive in this situation. That's the only way it could work without getting an imaginary solution. Alright, so that's a little bit unusual. The way that shows up, the way those absolute values show up, is whenever you have an even index, alright, of an even power, your absolute value is going to show up. Now there are actually some situations where the absolute value will show up and then it will no longer be required as well. In this case, it was still required. Let's see if I can... Let's see... I think I will be getting a problem like that a little bit later on. And then it turns out you don't have to have just fractions with numerators of 1 in the exponent. You can also have kind of fractions that are not just 1 unit there, but I mean even something like 3/4. And once again, the way this would work is I could break the denominator into being the index of a radical, and the numerator is still just going to be an exponent. So I guess I could, one of the things you might not know is 5 to the 4th is the same as 625, right? And then if I multiply those exponents, that's just going to be 5 to the 3rd, or 125 in this case. So, so kind of some interesting situations there. You similarly, with some of these, you can, with rational exponents, apply our other properties. So what if I have 16 to the 3/4 over 16 to the 1/4 power? So I'm dividing two fractions, right? So I would subtract the smaller exponent from the larger. So that would be 16 to the 3/4 minus 1/4. In this case, we're lucky that these happen to have the same denominator. So that's 16 to the 2/4, or 16 to the 1/2. And then what is 16 to the 1/2? Well, that's the square root of 16, which is 4. All right. So all other properties apply, regardless of whether or not my exponents happen to have radicals in them, or sorry, fractions in them. And then, so with these, I can actually sometimes simplify without, I mean, I also could have, I guess, taken an alternate route here, where I could have thought of 16 as being 4 squared to the 1/2. So that's 4 to the 2/2, or 4 to the 1st, right, which is 4. So you can work within the realm of radicals, or you can work within the realm of just exponents if you were interested in that. And then let's see, another example. What if I wanted to simplify? What if I have the square root of r to the 7th, s to the 25th, and t to the 3rd? So in this case, I'm taking a square root, so I want to try to, I could rewrite this as a fractional exponent of 1/2. And I will be interested in actually, I usually think of these problems in the worlds of radicals. So the way I would do this problem is I want to try to break these up into their largest, I guess, exponent that's divisible by 2. So I would think of this as the square root of r to the 6th times r to the 1st, which I'm kind of using one of our early properties we did. The first one, multiplying two things of the same base, you can add the exponents. I'm actually using that in reverse there, right? 6 plus 1 is 7, right? So that's kind of how I did that. Let's see, the largest number that 2 goes into that, or sorry, the largest number that goes into 25 that's divisible by 2 is 24. So I'd break that up into s to the 24th times s. And then I'd break the t up into t squared. That's not supposed to be a minus sign. T squared times t to the 1st, right, is also t to the 3rd. And now I can square root all of these even ones, and keeping in mind the idea of fractional exponents, right, that's just going to be dividing these exponents in half, right, because I could have thought of this as a 1/2 power that I'm distributing in a sense. So the square root of r to the 6th is r to the 3rd, and because this is an even root, an absolute value shows up. I'm going to just simplify the ones that I can take out first. Square root of s to the 24th would be s to the 12th, and an absolute value would show up because it took an even root. And the square root of t squared is just t, and an absolute value would show up. And then I'm multiplying that by who's left on the inside. I've got r, I've got s, and I've got t, right? R, s, and t. Those were not divisible by 2, right? The index. or their exponents weren't. And now, looking at these absolute values, one of these absolute values is actually not required. It's redundant. And I'll explain why. It turns out the s to the 12th power, because this exponent is even, if s was negative, raising it to an even power would make it positive anyway. So I don't need to say the positive version of this positive number. It's redundant. So I'm going to actually separate s to the 12th out of the absolute values. I'll write the other two things within the absolute values there. And then I'll have the square root of RST. All right. Now there are ways that you could have done this problem using all just exponents. I could have converted this to 1/2 power and done it all from that perspective. I kind of like the radicals myself, but it doesn't matter which way you use, as long as you are very careful about your absolute value stuff. And let's see, one more thing with real exponents to consider. So far all we've been doing is simplifying problems. What if I wanted to solve a problem? What if I wanted to solve the equation 734 equals x to the 3/4, that actually looks almost like a lambda, plus 5. So in this case, because I've only got one variable, I would isolate it, right? So I'd subtract 5 from both sides. Let's see, that's 729 is equal to x to the 3/4. And now I actually could write this as the 4th root of x cubed, or different things like that. But I think what we'll do is work within the realm of powers and exponents. I could get rid of the 4/3 power, or sorry, 3/4 power by raising it to the 4/3 power. Right, by raising it to its reciprocal. When I multiply, this would cancel out with that would cancel out with that, and I'll just get x to the 1st. Right, so that's what I get over here, is just x to the 1st equals, and then 729 to the 4/3 power. I think 729 is a cubed root, if I'm not mistaken. Yeah. So I could actually have written this as 9 cubed, all to the 4/3. All right. And when I multiply those exponents, let's see, I'm going to flip this now. I would get 9 to the 3's would cancel out, and that'd just be 9 to the 4th, which is 6561 is the answer there. So that's how you can solve those like that. I guess my alternate path would have been, I could have written that as the 4th root of x to the 3rd equals 729. And you could have raised both sides to the 4th power. And then I would have been left with x cubed equals whatever that is, and then I would have cubed rooted both sides. And you could have kind of undone it one step at a time to eventually get x by itself as well. And actually, in terms of these fractional exponents, not only could I have written it as the 4th root of x cubed, I could have thought of it as the 4th root of x all cubed is another way I could have done it. And then I could have cube rooted both sides and then raised both sides to the 4th power to get my solution as well. And that would work as well. So there was a quick review of a whole bunch of properties of exponents, of radicals, of solving equations with rational exponents in them. And yeah, just a quick review. I guess in Algebra 2, this could have possibly been, half a chapter's worth of material, but we just did it in under 20 minutes. So if you do have further questions on this, I would recommend you looking up properties of exponents, properties of radicals, rational exponents, and things like that, so you can get some further practice if it was needed. So thank you very much for watching, and have a great day.